Gauss's law provides us with a method to calculate the electric field around highly symmetric charge distributions in a relatively simple way. Here we will look at the electric field outside a uniformly charged rod. If the rod is uniformly charged, it implies that it's got a uniform amount of charge per unit length. So the amount of coulombs per unit length is constant all over the rod. To get an idea of the direction of the electric field at a distance a from this rod, let's look at the contributions to the electric field from two tiny segments of the rod, one to the left and one to the right of the point A. These will produce two electric fields as shown, which, if we calculate the resultant electric field, produces an electric field that is perpendicular to the rod itself. Since the rod is infinite, it means that for every contribution from the left of point A, there will be an equal contribution from the right of point A, which will produce a total electric field that is perpendicular to the rod. Also, because the rod is infinite, it means that all points along the length of the rod are exactly equivalent. Therefore, everywhere along this rod, we expect the electric field to be perpendicular to the rod itself. We can now utilize this symmetry when we choose a Gaussian surface. First of all, we note that for all points on the dashed circle with radius a shown on the screen, the rod basically looks the same. We call this axial symmetry. Therefore, we expect the electric field at all points on the dashed circle shown on the screen to also be the same. Therefore, we expect the electric field to reflect the symmetry of the charge distribution. Therefore, the electric field at this point and that point are all perpendicular to the rod and have the same magnitude, since all these points are at the same distance away from the rod. If we now choose a cylindrical Gaussian surface to enclose a portion of the wire with length L, and we look at the electric flux that passes through the surface, we realize that, first of all, the electric field is everywhere parallel to the flat sides of our Gaussian surface, which means it's perpendicular to an area vector on that surface, and the electric field is perpendicular everywhere to the curved surface of the Gaussian this Gaussian surface that encloses the portion of the wire. The total electric flux through this surface is now given by the electric flux through the flat surfaces plus the electric flux through the curved surfaces. However, the electric flux through the flat surfaces is zero because everywhere on the flat surface, the electric field, being perpendicular to the rod, will be parallel to the surface itself, which means that the electric field is perpendicular to an area vector constructed anywhere on the flat surface. So the integral of the electric flux over the flat surfaces will add up to zero. This implies that the electric flux through the entire Gaussian surface is completely determined by the electric flux through the curved cylindrical surface. And whatever this number is, it has to be equals to the amount of charge that is enclosed by the Gaussian surface. This is just equals to the charge per unit length multiplied by the length enclosed by the surface. From the symmetry arguments we presented earlier, we know that everywhere on the curved surface, the electric field, being perpendicular to the rod, has to be perpendicular to the curved surface. In other words, it will be parallel to a surface vector that is erected on the surface itself. Therefore, the dot product E dot dA simply evaluates to the multiple of the magnitude of the electric field and a tiny little surface element dA. Also, from the axial symmetry of the rod, we know the electric field will be constant everywhere on the curved surface, as all these points on the curved surface are at the same distance away from the rod itself. Therefore, we can take the electric field out of the integral. Now, the integral of all the elements dA over the curved surface is just equals to the curved surface area itself, which in this case is equals to 2 pi a times the length of the cylinder. So we've got on the one side expression for the electric field and the surface. On the other side, we know this is equals to the charge enclosed in that surface divided by a constant. If we solve this equation now for the electric field, we end up with the expression shown at the bottom right.